This is a lecture that's going to go along with your notes for the average value of a function, which is page 3 and 4 of your notes. And that homework, the homework you can find on page 4 of the homework is the average value of a function. So the essential question for today is how does the definite integral relate to the average value of a function? So if we look at the title of this unit, average value of a function on an interval. First of all, we need to kind of be aware that we're talking about an interval. So we're talking about a beginning and an end, a definite defined domain, and average value means we want to try to find something that is somewhere in the middle over the whole function values. So if we look at a couple of representations of that, the average value. If we start with this definition here, it's written twice, but I'm going to focus on this up here with this definition. So the average value of a function is a constant function. It's a horizontal line. So in other words, the average value is something that we find that is a y value. And it would yield a rectangular region having the same width and area equal to the value of the integral of the original function. So if we take a look at this original function here, which kind of looks like a parabola, its area, or its definite integral, is 12. So we want to find a rectangular region, so it says over here, rectangular region with equal area. So we need to make a rectangular region between -2 and 3. We need to make a rectangular region with area 12. So it's got to have the same width. That's why I said it needs to be between -2 and 3. So here's the same width. So it's got to be this wide between the green lines. And we got to have this area equal to 12 here. So that is what the average value is. The average value is the value that we need. It's basically the height of this rectangle that we create that has the same area as that definite integral. So if we look at this geometrically, since we do know the area, we could just say that we're looking for the height. And the height is going to be the area of that rectangle over its width. Well, the area is 12. Its width is, if you count here, this is 2 and this is 3, so the width is 5. So the height has got to be 12 fifths. And that's exactly what the average value is 12 fifths. So let's kind of go back and tie this to calculus then. This is a very geometric definition of average value. Okay, so to tie that to calculus, we're going to call this average value instead of height. The area is the value of the integral, so we're still going to call that the area. It's just the area under the function, and then the width is the domain width of that function. So for this example, 12 over 5, that means the average value is 2.4. So that means we have this function, f of x equals 2.4, and that 2.4 represents that average value, that height that we need so that we create this rectangle that has the same area as the definite integral. So to officially fill out the definition then, we're going to say that the average value is the value of the definite integral. Okay, so we're going to look at the I can go down here, the value of the integral. So this is f of x here. We're going to evaluate f of x between a and b. So that's the value of the integral. And it's got to have the same width, so we're going to divide that. There's the integral. We're going to divide that by b minus a. So if we go back up to the example at the top of the page, b minus a is 3 minus a -2. That gives us a 5. So this is our definition of our average value in relationship to calculus. And so we can find that average value and draw that line across the graph. And we can see that we're kind of recreating this picture up here. We can drop down these sides of our rectangle that has equal width from A to B, and we can color in that rectangle. We know that that rectangle has the area, the same area as the value of the light blue region. So you might want to pause the video. I'll go back here. You might want to pause the video to get these notes down for the definition of average value. Looking at this example here, I can give you a real geometric example where the values of the areas have already been determined for you. And if you notice, we're dealing with now a function that goes both below and above the horizontal axis. So we've got to tie in, what that means in terms of the value of the definite integral. So the average value here is we need to have the value of the definite integral of function g of x from -7 to 5, right? Because -7 is where it starts and 5 is where it ends. So we need to have the value of that definite integral, and then we need to divide it by 5 minus -7. So this whole region that starts over here on the left, -7, and ends over here on the right, 5, that whole region has a width of 12. So and this is where it differs from plane geometry, because geometry treats area as always positive. We know that this definite integral can sometimes be negative. And all that means is that our average value is negative. So if we look at that, we can figure out the value of this definite integral. These values inside the regions are the values of the integrals. So we have -5 plus 3 and -8. So the value of our integral is going to be whatever that algebraic answer is, and then divided by 12. So when we do this math up here, we get -10 over 12, which means our average value, if you want to reduce that, is -5/6. So what that means geometrically is that this is the height of our rectangle. The negative sign just means it's down here in the third and fourth quadrant. So there's the average value at -5/6, and it extends from -7 to 5. So that's our average value. And so when we talk about area, I'm using my air quotes here. We're talking about the value of that definite integral, and that can be sometimes negative. And when it's negative, we have a negative average value, and that means that we're talking about creating that rectangle down here in the third and fourth quadrants. And again, if you need to pause the video to finish up those notes, go ahead and do so. Sometimes we don't even work with a graph, though. We just work with the definition of average value. So average value is the integral of the value of the definite integral from -2, in this case from -2 to 7, over the width of the domain, which is 7 minus -2. So think about starting at -2 going to 7. That's going to be a width of 9. And we could draw this out if we wanted to, but we don't have to. We can evaluate this definite integral by anti-differentiating it and then evaluating it at 7 and -2. So essentially what we're doing is we're evaluating this definite integral. We're using the fundamental theorem of calculus, part 1, right? We're coming up with the antiderivative, and we're coming up with big F, right? We're plugging in 7 and we're plugging in -2. So it looks kind of like this. Antiderivative of sine of x is minus cosine x. I'm going to evaluate that. Remember, the vertical line means evaluate from -2 to 7, and I'll divide that by what I'm going to eventually call 9. So I'm going to go ahead and plug in the upper and the lower bound. Again, in the numerator, all I'm doing is the fundamental theorem of calculus, part 1. So negative cosine of 7, plugging in the upper bound. Remember, top bound's always first. And then we subtract the lower bound. This is going to get messy because of all the negative signs. So it's going to be negative cosine of -2. So if you notice, I'm using a bunch of brackets there, just to separate what's happening out all over 9. And so now this is the answer. So if this were a free response question, I would tell you to stop right here. That's a numeric answer. Cosine of 7 radians is some value. Cosine of negative 2 radians is some value, right? The negative 2 just means we're going around the unit circle backwards or clockwise. So that's a numeric answer. We just leave that alone. But we can clean it up. And the only reason we would clean up this answer is if we were answering a multiple choice question. So let's talk about some identities for trig values. So if you can envision a unit circle, I'm drawing it kind of in the air here. I'm going to actually draw it down here in the air because I'm going to put some stuff up there, right? And here's my vertical axis and my horizontal axis. So here's the center of my unit circle. Cosine of negative 2 means I'm going, again, here's my circle, I'm going backwards 2 radians. Now 2 radians is smaller than pi, right? Pi radians is 3.14. So if I go backwards, I'm probably somewhere in the third quadrant. If I go backwards, negative 2. So I'm in the third quadrant, but if you think about it, the cosine of a negative radian value is the same as the cosine of the positive radian value. So in other words, if I go backwards negative x, or if I go forwards positive x, I've got like 2 points that are right above one another on the unit circle, so they would have the same cosine, or they would have the same x coordinate. And just to put it out there, that's what we're going to use for this example, but the same thing happens with the sine. If I go backwards x radians, or if I go forward the same x radians, I still end up with those dots right above one another. And that means, since the sine is the y coordinate, if I change the way I go around the unit circle, that just means I've gone from above to below, or below to above. And all that means is I've taken the opposite sine value. So the sine of changing my direction of negative x is the same as the negative sine of x. So that means that this negative cosine x of negative 2 really just becomes minus cosine of 2. And so I can really clean this up a lot. If this becomes minus cosine of 2, the minus sign is still right here, then this minus a negative becomes a positive. And so I can really clean this up by saying this whole thing minus negative cosine of negative 2. That whole thing is just cosine of 2. And so I'm going to write that first because it's positive. So this whole numerator becomes cosine of 2 minus cosine of 7 divided by 9. So that's how we can clean up that answer. And again, we would only clean up the answer if we had to identify the correct answer on a multiple choice question. So I've given you 3 examples, some very geometric, some more algebraic, and that should be enough to help you with the con homework or any College Board quiz I might give you in the future. So getting back to that essential question, how does the definite integral relate to the average value of a function? We know that the definite integral provides the value of the area needed for the numerator of that definition, right? We look at that definite integral, that number, we stick it in the top, and then we find out how wide the domain is, and we divide out that, and that's how we get our average value. So for today, get this done right away so that you can get it off your plate of things to do. Go into con and do the average value of a function practice.